document. We already downloaded the crypter tool and the debug symbols and also the encrypted document itself. So let's have a look to see if those documents are still here. Let's maybe make a new directory, elf scroll, and move elf scroll into elf scroll. It might give us an error that it can't move itself. Yeah, that's okay. Oh, no, it's not. Elf scroll dot star into elf scroll, and we also have the encrypted document as well, which is elfu research. So I'm going to move the elfu research in there as well. Elfu research PDF. Let's see, elf scroll. All right, so we've got our three files here, an executable here, Windows executable. We've got a PDB and the encrypted PDF, I guess, .pdf.inc. So I'm assuming that's a PDF file. And what is the middle line on the cover page? So we're given three files: elfscroll.exe, elfscroll.pdb, and a encrypted file called Elf Research Lab Super Sled-O-Matic Quick Start Guide, version 1.2. Now this is very likely going to be a PDF file because it's called .pdf.enc, which is probably stands for encrypted. So our goal is to decrypt this file. And we are given the original tool that was used to encrypt it. So let's have a look at the tool and do some static analysis first, and then do maybe some dynamic analysis to see what happens during the encryption process. We could use IDA Pro. There is a free version that we could use on Windows, but I'm going to use Radare2. Radare2 should be able to, disassemble this file and get some of the symbols as well, because we got the PDB. So the debug file, the symbols file, is included in this challenge. So we can use IDA, or we can use another any disassembler or debugger should be good for this one. So let's use Radare2, which is R2. It's installed by default on Kali, or it should be. And elfscroll.exe. All right, so this is apparently our entry point, the address for the entry point. So one of the things that you want to do first is analyze the file. So that's a lot of A's. Interesting enough, if you put a lot of A's there, there's a bit of a joke there saying that a developer is coming to your place to analyze the program for you. So obviously we're not going to wait for that. That's not going to happen. So now that we've analyzed the file, we can do a function list. So we'll display all the functions. So we can see a few functions here, and they're not very descriptive, so we don't really know what the functions do yet. Let's have a look at the imports. So you can have a look at the imports by pressing II, and we can see the imports here. So the two main things that I like to do at the beginning of analyzing an executable is a function list to see what functions there are in the program, and a list of imports. Because ultimately, most modern programs are effectively at their core just scripts that put together a lot of API calls. And once you realize that, most source codes are actually not that long anymore. You don't get thousands of lines of code anymore. You might get 20 lines, 30 lines of code. And what happens in that code is a lot of these external functions are being called, like crypt import key, read file. So that's doing all the file reading for you. So you basically use this external function, which is imported from this DLL file, dynamic link library. Get tick count, and so generally the script uses these API calls, and you can get a pretty good idea of what this program would do just analyzing the imports. So if we have a look at the imports, we can see here crypt import keys. So that's probably going to import our key. We're going to do some crypt decrypt. So it's able to decrypt something. It can encrypt something. It does some file reading. So we might have a file that we can read, for instance, an encrypted file. Or a non-encrypted file that we want to encrypt. There's a get tick count here that's getting the amount of ticks elapsed since a particular time, 1970, I think, on these kind of PCs. We've got a sleep call here, and we've got some internet calls here. That's always worrying when you see a small program like this that's got some kind of HTTP connections or reading from the internet. Why does it need to read from the internet? All it does is encrypt or decrypt files. Why do we have these calls? So I guess we'll find out a little bit later. We could analyze these calls statically and see what they do, but we can always just run the program and see what it does, because ultimately we trust who sent the program to us. It's Santa and SANS. They wouldn't send any malicious files, or if they do, they let you know about that. So I'm going to trust the file. And also, if anything does get infected, this virtual machine that I'm on at the moment, this Kali box, is completely segregated from my personal environment, personal network. So even if something does happen, I can just revert the box back to a known good state. So not too worried about running any kind of malicious files on this box anyway. Let's just run the file and see. So we should be able to see a lot of these API calls actually being used while running the file. So based on the API calls, I would say it reads the file, right? It then encrypts the file, and it will send you a message somewhere, I'm sure. Just some string comparing. I'm not sure what this internet open does yet. I'm not sure why it needs the internet. So let's have a look. Let's run the file and find out. So if we quit the Radare2 using the Q command, we can now run the file. Now file elf scroll .exe. We can see that the files are PE32 executable. So if we try and run that, chmod plus X to make it executable. If we try and run elf scroll, it won't work because it's not a Linux binary. It's a Windows binary. So one of the ways to run that is to run wine and then elf scroll. And wine is not installed, so we need to install wine. There we go, 255 megs. Hopefully it doesn't take too long to get the wine. Now that's the decompressed size. So usually, the download's about half that. So I imagine it, the total download would be about 100 meg for wine, maybe even less. And there you go, it's already installing. So once wine is installed, we should be able to run the executable and see what it does. Now if this executable for whatever reason doesn't work on Linux Wine, then we will just run it on a Windows machine. But for now, let's see if Wine can run it. It seems to be a fairly small file. So the way to run it is wine and then elf scroll.exe. Bad exif format. So we'll try one more time and see what happens. Looks like wine32 is missing. We should install that, so we need to enable the multi-arch first. So let's run this command here, copy selection and then paste clipboard. And our repository is not valid yet, so we'll need to find out how we can get this repository valid. So it says invalid for another 1 day and 12 hours. So let's do a date, see what the date is. Tuesday 7th of January. I think our time might be off, so let's set the date. And let's do a date again. Let's try the apt-get and see if that fixed the issue. So certificates will get the local time versus the time on the server, and it says invalid for another 1 day. So let's have a look. I think it's got something to do with the time not being accurate. So it seems other people are having this issue as well. All right, so we might have to set the time against the date. Let's have a look, and it's setting it back to 7th of January. So it's getting that from somewhere. We want to make sure that NTP is working. We need to enable the NTP service. So let's have a look. If we start NTP service, if our date is changing, and no, it isn't. Not yet anyway, it might take a bit of time. Let's make sure we install the right NTP. Oh, here we go. Set NTP. Let's set that to 1. Hey, there we go. All right, so now our time has been updated to Thursday. And let's do an apt-get update. So on your machine, you might not have to do any of this if your time is already correct. But if it isn't, then you might have to do the same thing. So let's have a look and see if it is able to download the packages. So it seems to be downloading something, so it seems to be okay now. So let's try this one again and see if we get rid of that error now. Oh wow, okay, so almost a gig worth of downloads, or at least of additional space. So I would imagine 500 megs of downloads. I'll stop the video here and then get back when all of this is fully installed. Okay, so that didn't take too long. It took about 5 minutes and everything seems to be installed. Didn't get any errors. So if I scroll up, you can see pretty much what happened. Yeah, so a lot of installations happened there. So we should have installed Wine 32 now. So we've got Wine 64 and we've got Wine. Do we have Wine 32? Minus version. I'm going to assume that Wine is now 32 version and Wine 64 is 64. But let's give it another run and see what happens. So this one here. Now hopefully Wine is 32 bits and Wine 64 is 64 bits. Oh, there you go. So now we're getting the welcome message. Welcome to Elf's Grow, version 1.01. Okay, so we can encrypt or decrypt a file. You're encrypting a file. Try encrypt, for instance. All right, so let's try and create a file and encrypt it. So let's echo test to test.text. I'm just going to call it text. There we go. Now let's do cat test.text, and there's just test in there, right? So if I look at the actual bytes in there, let's have a look at the bytes are. So we got a little 0A, which is a new line character, so that's okay. So we've got 5 bytes in there, 1, 2, 3, 4, 5. And let's try and encrypt this and see what comes out. And by the way, this 0A is the reason that this jumps here. All right, so we do cat test and you see test here. And then we don't get the root Kali straight after here. And that's because the 0A character is interpreted by the bash to go to a new line, which it does. So it's nice formatting. Anyway, let's try and encrypt the file. So it says we need to type elfscroll --encrypt. The in file will be test, and the out file, let's use the same kind of way that the original file was encrypted with .enc at the end, and let's see what happens now. All right, something went very wrong. Crypt acquire context failed. All right, so maybe I can't run this on Kali after all, unfortunately. That's all right, we can run it on Windows. It probably requires some APIs that Wine might not support, or so let's do a quick Google and see if there's something we can do about that error. I'd really like to run the whole thing in Kali if possible, but you know, if we need Windows, that's fine. We can run it on Windows. So let's do Wine, because it's a Wine issue probably, and let's see. So Wine crypt. So crypt is part of ADB API. There we go. Yeah, so there's some unimplemented functions. This is LSA secret. It seems to not be able to acquire the context of the crypto. So let's run this in a Windows environment and see what happens then. All right, so I've copied the file elfscroll.exe to a Windows machine, and let's see if we can run elfscroll from this machine. Yeah, no need for Wine obviously because it's already running on the Windows machine. So let's create a file and encrypt that file and see what the end results are. So if we do echo and then test to test.text, and I'll have a look at format hex. Let's have a look at the contents of that file. All right, so we can see it used Unicode to put T and then 0 and then the E and the zeros here. So Unicode is not the file format that I want, and there's a reason for that. I want to try and keep the total amount of bytes in here below 8. Because depending on the block size of the encryption cipher, you can take a good guess at what type of cipher is being used just by seeing what block size is generated. Now, if that doesn't make any sense, we can just test it out. We can have a look and I'll show you what I mean with that. So let's remove test.text again. And then instead of using the format, so the echo test to write, I can use PowerShell as well. So PowerShell uses set content, and we're going to write that to test.text, and we're going to write what? Value test, right? All right, so now if we do another format, we can now see that we have less than 8 bytes. Now you can see here that the 0D and 0A, that's enter a new line. So if you want to remove them, we can simply do, here, no new line, and that then removes the 0D and 0A from the text. So we only really have the 4 characters in there, so the size of this file should be 4 length, right? 4 bytes, 1, 2, 3, 4, which we can see TEST. So this is a perfect test file for us to play with. And let's try and encrypt this file. Right, so we do elf-scroll -exe and then encrypt. In file is test, and then out file is test.txt.enc. All right, that's a lot better. So this Windows machine was able to create the key. Now, before I tried this in Wine and it says crypt acquire context failed, probably an API call that was missing here or some kind of environment, or I'm not sure exactly what causes this, but to try and diagnose this error instead of just running it on Windows, it's easier to just run it on Windows. So this is what we get. So I'm going to take the output here and copy that into a text file on my VM. All right, so, and before I do that, I need to enable the copy pasting in the VM. So I go here in a shared clipboard and I do bidirectional. So now I can copy paste from here, so to my Windows, but also from Windows to there. So if I copy this, so I just select it and press enter, that puts it in the clipboard. And then if I go here, I should be able to paste that. There you go. So that's the shared clipboard that I've just enabled via the devices here. So that's now enabled, so I can copy from the guest to the host and from the host to the guest. So 2 more things that we need apart from this output is we need the actual bytes that were originally encrypted, so those ones, and we need the actual encrypted bytes. So here we go. Let's take this output here and put that in a text file here. All right, so that looks pretty good. We've got the command, we know what it does. So we can now use this text file and let's actually save this, save as SANS, and we'll save that as elf-scroll.txt. There we go. We can now close this PowerShell window. We don't really need it again. One thing I'd like to do is just to try and decrypt to see if we can decrypt it again. So let's have a look at elf-scroll, how we can decrypt. So we can decrypt using the ID, secret ID, and then in file, out file. So the ID, what's the ID? Your secret ID is this. Don't share that key with anybody. All right, so let's do that. Let's delete test.txt to make sure that it's not there anymore. And let's decrypt the file just to make sure that everything works. There's nothing broken. ID equals, and we've just copy pasted that. So that's the one. I just press the right mouse button to paste that. And then the in file will be test.enc, and then the out file will be the same one, but then without the enc. So let's have a look. So it's retrieving the key from an API. So this is probably where that HTTP call is being made. It then retrieves the key. We found your key, file successfully decrypted, and let's have a look if that is true. So if we do a type test.txt, we get test. Perfect. So we have an encrypted file here. If we type .enc, it'll probably give us garbage. Yes, so that's the garbage that we get. So we know that encrypting the file works, and then decrypting the file works as well. So let's have a look at the intrinsics of how the encryption works and go from there. So we can close this PowerShell window now. And we have our output here on the elf-scroll.txt. So this is the command we use, encryptist. It says, let's format it a little bit. Welcome to elf-scroll. Menus elves are putting together random bits for your secret key. It then says it gives us a seed. Now, if you've been a blue team or worked with some log files, you would recognize this number perhaps. To me, it looks like an epoch time. So 1578, definitely epoch time. Epoch time is sometimes used for log files or for time generation. But even if you don't recognize it, that's fine. We can analyze the binary. It then generates an encryption key. So this seems to be the encryption key it generated for that file. Elf scrolls the key. Okay, so it's saving the key to a website. That's where that HTTP is used, and then it's elf scrolled it to here. Gives you back a key, so you can then retrieve the key to get your original encryption key back. So the ID. Right, so we have an encrypted file. So if we are able to somehow retrieve the secret ID that matches that file, then we would be able to download the original encryption key and go from there. Now, the seed value is an interesting one, because if we can have a look at how this random number is generated, we can maybe create our own random number, right? So it says seed is this encryption key. So I think the first thing we'll do is we'll try and write a Python script to decrypt these bytes and give us this result, because we have the encrypted text, we have the decrypted text, so we know what the results should be, and we also have the key here. So we can write a very simple Python script to decrypt the encryption. So let's have a look at what type of encryption is being used. Now we've got the original text was 4 bytes long, 0, 1, 2, 3, right? So 4 bytes. And the encrypted text is 8 bytes. In other words, 64 bits. And there's not that many encryption methods, not popular encryption methods, I should say, that use 64 bits. For instance, 128 bits would be AES, 64 bits would be DES, those kind of encryptions. So let's have a look at the source and see if we can find what type of encryption is being used to encrypt this. And then based on the suspected type of encryption, we're going to try and write a decryption file in Python. So we open the file in Radare2, and if we analyze the file first with AAA, we can list the functions. So the functions don't really give us any hints of what's happening yet. There's a exit function here. It probably exits the executable once it's run, but the imports tell us a lot more. So we can see here HTTP send request query. This is all that ELF scrolling. That's being done using these APIs here. Get tick count might have something to do with getting that time. And then we've got crypt, encrypt, crypt, decrypt. So let's have a look at the encryption algorithm used, because once we find out what encryption algorithm is used, we can try and write a simple decryptor for the information that we already encrypted, which we have the clear text of. So now the way to find out which functions or which calls are being made to these destinations, right? We want to know what accesses this particular memory location, right? So what calls this? There's a command in Radare, axt, which will show us which functions or which calls are being made to this address. So we know where this, where this is accessed. It gives us this function here. It says, well, this function here is trying to access that address. So let's have a look at this function and see how we go. So if I do a S for seek and then paste that address, You can see now the prompt changes to this number, right? This is the one we seeked to. So this is where we currently are at inside the program. So our prompt is there. So just like a prompt on screen, let's have a look, see if I can put it forward here and backwards. The location of our prompt in the program is now 0 times, which is hex format, 00402.6D0. That's where we are at. So if I type the visual mode, VV, I should be able to see the function. And again, this is the location we're at, right? 4026D0. That's where we seeked before, and I can show you that. Right? 4026D0 is where we seek. This is the address, and if I type VV, we will be at this function address. Now we know this function, based on our AXT command earlier, calls decrypto. So you can see here, Microsoft Enhanced Cryptographic Provider. This would be debug information coming from the PDB file. So we can see here, crypt acquire context. And this was the issue we saw earlier. Crypt acquire context failed. So something here would have gone wrong. So ADV API 32, and then it tested EAX to see if there was a result there. It would have jumped here, this green one here, to here if there was no error. And if there is an error, it would go here. And probably this call would do some kind of an error of some kind. Now we can have a look at what this call does by pressing G. Right, this will go somewhere, and an fcn.00401 cc0, right? So this will go into this call here to see what this call does. And again, code is nothing more than script. So ultimately, we're just looking at the API calls to get a very quick glance at what's happening here. We don't need to understand the full code with all the pushes and all of this stuff here. It's very rare that people actually code these things directly. They usually just go via an API of some kind. Something went very wrong. That's not supposed to happen. This is the error message that we got, right? So this just seems to print or handle errors. One of the things we can do is we can rename this function. So press D, then R, which is this option here, rename function. And we can rename this to something more user-friendly, more memory-friendly. So output error or handle error. I'm going to call this handle error. Okay, now you can see that this function is now called handle error, right? Because this does some kind of error handling here. Maybe print error would have been better, but either way, it's good enough. Now I press U to go back to the previous function. So I press U, which gets us back to the previous function, which is 4026D0, right? And here we can now see that it's calling handle error. So renaming this function has given us some context of what happens here. So if this call here goes wrong, it handles an error, prints an error. Maybe I should have called it print error. Either way, let's proceed. We now know that that's some kind of error handling thing. If everything works right, though, it'll go right around this error and go straight here. So we need to find out what this does and what this does, etc., etc. Now, based on this string here, generated an encryption key, we know that between here, where it tries to acquire the crypto context, and here, we are doing something that generates the encryption key. So the only thing that happens between here and here is this function here, right? fcn00401df0. So it's very likely that this function here generates the encryption key. Anyway, we'll have a quick look through this function to have a look what the overall thing does. It tries to acquire the context. Once it's acquired the context, it imports a key, which probably is generated here, but we'll analyze that later. Once it's imported the key, again, handle error. So if it goes wrong, it'll just handle error. It goes around here, and then it encrypts something, a file, for instance. All right. If that goes wrong, again, handle error. So we then go here and successfully encrypted a file, right? So we get a bit of an idea of what this function does. So let's rename this function to something more more useful, more friendly. So let's do a D and a R. What shall we name this function? Something like file encrypt. Doesn't matter what you call it, something that makes you remember what this function does, and it's kind of a summary of all the actions here. So it takes some kind of a key. It actually creates a key as well, so maybe we should add that to the description. But I think it's good enough. File encrypted. Ultimately, it encrypts a file right at the very end. This is file encrypted. So that looks pretty good. Now, is there anywhere where we can see the type of... Oh, yes. Let's have a look here. So it tries to... Crypt import key failed for DES CBC, right? So we can see DES CBC is very likely the type of key that's being used here. So DES is a type of encryption, and DES actually does use 64-bit or 8-byte block length. So DES is a really good candidate, and cipher block chaining CBC is likely as well. So let's try and use this. Let's try and find some code that can decrypt DES CBC. Use the key that we got, use the encrypted bytes that we got, and try and decrypt that file that we created earlier. So let's give that a go. So let's write a Python script to do that. And we'll assume that the encryption is DES CBC. And we have all the information, I think, that we need. So let's quit out of this, and then we'll do some analysis later. I first want to write the Python script. We have the key. Right, so the encryption key. We have the data, which is this one, the original data, and we have the encrypted data. So with the encrypted data together with the key, we should be able to get this original ciphertext back. So the original text, not the ciphertext. So let's create a new file. Print hello. There we go. File save as. Let's save that in SANS, and let's call that. Let's save it in the elfscroll folder. Here we go. Let's call it decrypt.py. Now I always start with the minimum possible commands, minimum possible script length, and then go up from there and see, okay, well, you know, it's just the way that I work. It's small components, test them out, make sure that, you know, you don't build a big machine and figure out that all the parts might or might not work. Too much debugging. I like to start small and then build up from there. So let's execute this one to make sure that our Python works, that everything goes right. All right, so let's run Python decrypt.py, and that gives us hello. Okay, excellent. So that works. So let's do a search here for. Let's try and find out Python encrypt DES. Right, so that's ultimately what we're going to do. And here we've got single DES, which is what we're going to use. So we're going to use PyPy or PyCryptodome. So let's use PyCryptodome for this one. And we get a bit of a source here. So let's copy paste this. You can see keyword arguments. So we can use key, mode. So the key and the mode are required. We have some arguments on IV initialization vector. Is used for encryption decryption. If not provided, a random byte string is generated. So that's not a good thing for us, because we need to know the original IV value. So we might have to have a look through the source code of that elfscroll to see if the IV value is provided, a static value, or if it's randomly generated or whatever. So we'll have a look at that. So we definitely need to provide the IV at some point. But let's start simple, and let's just start with this and see what we get. Let's go back into our source code. So print hello works. So we just literally take this source code here. All right, let's leave the hello in there and just file, save, and run that and see what happens. All right, so we've got a IV must be 8 bytes long, so we have to enter some kind of an IV here, I guess. Let's just put an IV in there. So let's do B. So for byte array, so that's a byte array of 8 bytes, right? That's what it wants. IV is generated as an argument. So let's save this file here and try this again. This cipher instance has no attribute IV. Okay, so I think we're using the wrong des cipher here. Does it say anything about installing anything? PyCryptodome. Ah, here we go. Pip install PyCryptodome. So let's do that to make sure we're using the right paste clipboard, the right crypto API. All right, so it's successfully installed that. And let's try this again. Oh, I didn't want to install that twice. Here we go. As an attribute IV. So I think we can get rid of this one here now, because we modified this. This is the script that was given to us as a sample script. So let's see if that works. No, it says value IV must be 8 bytes long. So I don't think it's actually using the PyCryptodome. It's using some default package. So let's have a look to see how we can use the Kali use PyCryptodome. Okay, so it's it might be a package. Let's YOLO that again. So apt get install PyCryptodome. Let's see if that works. Nope. Let's do a cache search to see if there is a package. There is. So we just needed to have the right package. Python. It's already installed. Ah, okay, let's check the Python version. Yeah, we're using 2.7. So installation, it's already using that. So it seems that PyCryptodome is already installed, and interestingly enough, it doesn't seem like the example stuff here is working. Cipher.iv plus cipher. So where is that being set? Cipher IV. I think this this code isn't working because we're missing all kinds of information. So all right, so let's just write something that actually will work then. So if we do plain text test, that was our plain text, right? We'll do a mode. What's the mode for CBC? I'm going to guess that it is yeah, mode CBC. Mode CBC. So we've got a key. Let's use a much more easy key. 1 2 3 4 5 6 7 8. All right, needs to be 8 bytes. So we've got a key we've set that up. We've got a plain text. Let me put them like this. I like it better when it's all the variables are in one area. Cipher is technically also a variable, but whatever. Des.new, and then we've got the key, which is this one. I might actually rename that to bytes key because it's more descriptive. They are bytes after all. And then des mode CBC, so that's correct. And then message. Let's get rid of that IV altogether and then just try and encrypt something. And then print done. All right, this is the simplest encryption script that we can come up with. So let's have a look to see if that even works. We just want to get something working and then work our way up from there. So we're actually encrypting here, not decrypting. So we're encrypting. IV must be 8 bytes long. So I'm going to assume that we can put as an argument, so arguments IV, nonce. All right, so only applicable for these two, so we don't use any of these. We don't use any of this stuff. So we use mode CBC. So this, all this stuff is not going to apply to us. So the only thing that applies to CBC is the IV value. And it says that's a byte string. So it's used for encryption or decryption. So we are encrypting. It must be 8 bytes long. If not provided, a random byte string is generated. You must then read its value with the IV attribute. All right, so that's where that IV attribute comes from. It's randomly generated. Well, let's just generate it ourselves to make the code a little bit shorter. All right, so that's the IV right there. Let's try and encrypt again and see what happens. Input strings must be a multiple of 8 in length. Okay, well, that's a better message here. At least we fixed the IV issue. So let's do test, because that is now 8 bytes in length. File save, and then let's see if we do that. Then there you go. So it's done. So that seems to have worked. If we go into our text file here, and then we try and encrypt test, which we know is those bytes. So if we add 00000000, I'm just trying to see if I can get the same encrypted contents. So I want to see the contents in the bash to see if we can get the same contents using this encryption key. All right. So the bytes key will be this, because we know that that is the key that was used because it told us. So we're going to convert them to bytes. Well, they're byte values. We're just going to put a /x in front of it to make sure they are treated as byte values. So these are the byte values now. So this is our key that was used. We know that for sure because we've got the text here. So generate encryption key. Then we are encrypting that file. Now we don't know how it pads the file. This error here says the input string must be a multiple of 8. So somehow our block was 8 bytes as well after we encrypted it, right, using the program. And this is the proof, right? 8 bytes. So somehow the program has padded these bytes here, either with zeros or 90s or spaces, or it used something to pad these bytes. We don't know what that is yet, but for now, let's just test and see how far we get. All right. So we want to find that IV value. So this is just a random IV. I need to find in the program what the original IV was. So let's Google the function name. So all of this now seems to work. So we can go and start a new tab, a Google tab. Let's open up our program. Elf scroll.exe. Let's analyze it and list the imports. And this is, oh no, that's not the one, but it'll be in the same function very likely. This is the reference we're looking for. So paste clipboard. So let's have a look what function that is. So we might actually put this function in our text file as well, so we don't need to remember. So if we go here, so we can seek to that address, and we use VV, and we can see here the various function API calls. So we can see that as crypt acquire context, crypt import key. So this is where the key will actually be used. And this is very similar to our code here. Basically what this is doing is very similar to this, right? There's new, so it's creating this key thing. So because the key IV is in this function here, it's a very similar function here. I'll actually do a search for crypt import key. So we're looking for crypt import key function. Initialization vector or IV. After key is agreed, the initialization is set to 0 by default. Okay, let's have a look here. So it seems that it's set to all zeros by default. So let's go here, initialization vector. So they call it KP_IV. Points to a byte array. Specialization. This array must be block length. The block length is 64 bits. The IV consists of 8 bytes. That's consistent with the Python program we're writing here. It said 8 bytes as well. The IV is set by 0 by default. All right, so how can we set this one if not the default? So if this is not being set, set, there we go. All right, so crypt set key param apparently can set. Let's have a look here. DSS KPIV points to a byte, specifies. Let's have a look if that call is being made in the encryption tool. So we can go Q, and then look at the imports. So the only calls that are being made is crypt import key, acquire context, decrypt, and encrypt. So we don't see the set key param function. So to me that means that the IV, as per here, will be set to zeros. All right, so let's assume that the key is set to zeros. So let's start with that. So we'll set this all to zeros. All right, so x00, and I'm just going to copy that so I can count that 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 bytes. So that's the IV. As Microsoft Crypto sets this by default. We've got mode CBC as per the code here as well. We can't go up to see it, but we can actually. Crypt acquire failed. Import key for des CBC. So we've set the mode to CBC. So we've got the IV set. We've got the mode set, and we have the key bytes, and we have the plain text as well. So everything seems to be set for encrypting this. So let's encrypt this message and see what comes out. It was still called decrypt. Oh, we need to save it. We're actually encrypting, even though the file name is called decrypt at the moment. So our result was here. So now we're looking for a Y and these characters here. I think the padding might be different, so we can analyze the text, or we can try a few different values. Let's try spaces. Maybe it pads it with spaces. Save. Let's go into our prompt here. OI, no, that doesn't look like what we have before, so it might not be spaces, maybe dots. So there's a few different things it could pad it as. Let's try that. Now, if we can't get the same code, we can go through the code and see what it pads it with, the different padding mechanisms. You can also have a look here to see what bytes the crypt function pads it with. So let's have a look at that. So I can't remember what the crypt function was called. It's called encrypt, right? So let's copy that, and then we're looking for padding bytes, right? So that's padding bytes. The encryption uses PKCS1 padding. All right, so this is a type of padding that we can add manually. Let's have a look. So PKCS1 padding. There's a particular type of padding that is being used. It's a standard. So let's have a look. Apart from trying to get the PKCS1 padding value, we can also just use the encrypted value that we got, which we know is padded, and then try and get the original bytes back. Let's do that instead. We could try to find the type of padding that is being used, but let's make it even simpler ourselves and just decrypt the encrypted file. Because we've been encrypting, we don't really need to encrypt again. What we need to do is we need to decrypt to get the test plain text, right? So we don't care about that one anymore. We have ciphertext is, and then a byte array. So we can copy those ciphertext from here. So again, we start simple. The first thing I want to do is I want to just print the ciphertext, because that should look like the ciphertext here. It should look like this. If that doesn't look like that, then we already have a problem there. So let's save this and make sure that that looks the same. So we've got the key bytes and we've got the ciphertext, and let's just print the ciphertext in ASCII and see what that gives us. So save, and I'm going to close this Google page and exit from here, and let's do a decrypt. And there we go. So now we can see the Y here, Y, and then another Y. Let's make sure that looks the same. We've got a Y that looks completely different. Perhaps the bash shell is changing the look of the bytes here. I know that we've got a minus there. A minus is in there, this icon here. So maybe it is printing that just a little bit different. So we might have had it correct before anyway. Regardless, let's keep going. That looks to be the same. It's got one character the same. It's got this character the same and this one as well. The rest is unprintable probably in Bash, and it gives these question marks here. I'm going to assume that that's fine. I wouldn't be able to see how that would not be fine because we're literally taking the byte string here and printing it to the screen. So we're going to assume that that's correct. So now we're going to add the cipher, and the cipher is a des.new bytes key. We have the bytes key here. We know that that's correct because we literally copy pasted that from here. And we're going to put the bytes key in this new cipher with the mode CBC. We're going to use an IV of 0, and then we are going to print the decrypted ciphertext. So we're going to decrypt. We can probably do this. Plain text is a bit more readable in this way, I would say. So what we're doing is we've got the key, we've got the ciphertext, we've got our des mechanism here, and then we're using that mechanism to decrypt the ciphertext as plain text, and then we're just going to print the plain text here. So let's have a look at what happens and if we get any errors. All right, there we go. So that's done. We decrypted the text successfully. And it would be nice to see what the bytes were after test to see if we can get the original padding value. So I think the way to get that is we can do plain text and then encode hex. I think it was encode hex. Let's try that, see what happens. I think this will return the byte values. Yeah, there we go. All right, it is using PKCS1, which is basically the length of the remaining padding, I think. So 04040404. So had we entered plain text, and we can do that still here, plain text is bytes. Well, the good news is we've actually decrypted the text now. So test and then x04, x04, 04 and 04. So that's the padding that's being used. And let's try and cipher text cipher.encrypt plain text. And then we'll get rid of that print and I'll only print the ciphertext. So what this does is it takes the plain text, encrypts it into the ciphertext variable, and we're going to print the ciphertext hex values. So let's give that a go and see what happens. A6FC 59 D3 B3. So that's exactly this here. So by using the correct padding mechanism, using 4s here, we got the ciphertext to encrypt exactly the same way as the program does. So now we've got a Python script that can successfully decrypt encrypted messages, which is good, but we still need to know the bytes key. So let's just remove all the plain text things to keep our code small and run this one again just to make sure it still works. Yep, so we've got the decoded values right there. So that prints the hex version. Text. All right, now this will print out both the hex bytes and the text, which of course should just be the plain text. All right, test. There you go. That's looking good. We can decrypt a encrypted message. Let's have a look at the program to see how the key was generated. So we can have a look to see whether we can download the key from that repository, the API, or whether we can even maybe just reverse the used key at all. And let's have a look at Radare and see how the key is being generated. So R2 and elf scroll.exe. All right, so we'll analyze the file again, AAA, AFL to list the functions, but that doesn't tell us much yet. And then we do the imports. So II shows you the imports, right? The imports are effectively the bits of the DLL that it uses in its code. And like I said, most modern programs are nothing more than a Python script like source code, and all of the functionality comes from these APIs, and these APIs, with Visual Studio and everything that's included in Windows and Linux are getting really, really advanced. So the programmers need to do less. So you don't want to go through every one of these functions and check that the correct things are happening. You want to glance through these and see, okay, well, based on this, what does it do, and what am I interested in? So what we're interested in is the encryption function, right? So that's this one here. So let's copy that and go and have a look what calls this encrypt function. We can use AXT for that. Now, keep in mind, you can also do this using IDA Pro. There's a free version available, very, very powerful tool. But I wanted to do it in Linux. I wanted to do it with Radare and show that it is possible to do it with Radare fairly easily, just like with IDA Pro. So this is the function that is being called, FCN, and then 6D0 at the end. So copy paste that. And we're going to seek to that function. And then we're going to go visual mode to see what that function does. So we've earlier renamed this function, but that's disappeared. So in our reversing efforts, let's start naming some of these functions so we can, easier identify what's happening. So I think we said DR, and then this function name was file encrypt. Now let's go and have a look through these functions to see what happens here. Now this is an error message here, so I think for this function we had said that we can press G for go, fcn.00401cc0, that this function, dr, was some kind of error handling, right? So let's call it print error. It's descriptive enough. Press U for undo to go back to the previous function, which is our file encrypt function, right? So we're going to go here, call print error. That's now more descriptive than it was before. And we're just going to, at a glance, very high level, see what the APIs do and where our interesting bits would possibly be located. So we get crypt acquire context, and then we get here a string saying generated an encryption key. So let's have a look at what this function here does. FCN, so I pressed G there, FCN.004025540. And this is the printf function, so it prints something to screen. Right, and a printf here, some formatting, and it seems to be a fairly simple function to print something, right? So nothing complex here, no other calls anywhere except to fprintf. So when you're reversing or when you're analyzing a file, don't overthink it. Often on the job you won't have the time to look at every single function, what it does. If it looks like a duck, if it quacks like a duck, it probably is a duck. So we're going to say that this is some kind of print function. So we're going to press D and then R and then print message to screen, and then U for undo. So now we have a print error here, a print message, and the message is very likely this thing being pushed on the stack, which is generated an encryption key. So between this possible error here saying, you know, we've acquired the context for the cryptographic protocol, and this message here, we must have generated the key. So this function here is very likely generating our encryption key. And that's what we're after, right? We want to see whether you know, we can regenerate the key due to some maybe cryptographic error or vulnerability weakness, or whether we have to fetch the key from the server. So let's have a look at this call. So G and then fcn.00401df0. And let's have a look through this function, what this does. So else putting together random bits. Excellent. So this is generating random bits for the secret key. All right, so how does it generate that? There's a function here, there's a function here, and then there's a function here. So 3 functions are being called from this function itself. Let's call this function based on the information we have now. It's fairly reasonable to assume that this generates the key. Let's call this function generate key. All right, so because that's what it's saying here, right? I mean, it's putting together random bits for your secret key, or generate secret, or something like it. Just needs to be descriptive. So it prints something here. It's pushing this on the stack. I would say this is what's being printed out here. And then it does a call to this function. Let's go in there and see what that function does. Have a quick look. G and then fcn.00401e60. Very easy. This seems to get the time. So MSVCR90 times 64. DR. And let's call this get time. Get current time. There we go. And we can verify what it does by just going to a browser here. MSVCR90 and then time 64, right? That was the call. And then in the Microsoft Docs, we can see what that function does. There we go. So we got a pointer to the source location, returns the time as seconds elapsed since midnight, January 1st, 1970. And they call this epoch time. Now let's copy paste this, put it into our text file. Go back into our debugger. So this is get time. So it gets the current time since 1970. So it's that epoch time value that we saw, right? So let's go and press U. So now we see call get current time. Let's go into the next one, fcn.00401d90. And again, just look at the high level things, the green messages, right? So we're getting a some IOB, fprintf, so it just prints something. It looks like it's just printing something, seed, here we go. So it seems to be printing seed. Now if we have a look at the text file here, so we can kind of keep track of where we are in the program. The program starts, it says welcome, and then it says our else putting it a random bit. So this is kind of the function we're in. And it then says seed equals, and then a value, right? Seed equals. So this print function here probably prints seed equals, and then that decimal value here. This is what that prints. All right, so let's call this dr and then print seed, and then press U. So what this function does now, generates the key, right? It gets the time and then prints the seed value. So it's safe to assume that the seed value is based on this time variable, right? And let's have a look at what the current time looks like. So get time since 1970. Epoch converter. It see what that does. And 157. So let's go and copy paste this value here. So I've just copy pasted that, and that seems to increment all the time, right? So let's put the value we just copied here, compare that to the seed, and you can see the value is very close to the value that we used when we encrypted that file. It's very likely that the seed being used is based on time and time alone, and that is a very, very small starting point, seed value. If we had any idea of when this file was generated, 2019 sometime, we could severely reduce the amount of seed values and possibly create, regenerate the encryption key based on when this was created. Now, what does it do with this seed? So let's go and print seed. So now instead of a function address, I put in print seed, right? So I press G, print seed, and that should give me into the function for print seed. I just want to see where the variable is stored. So the time is at the end here. It says printf. It says showing the seed, but it also moves the value of the seed into this location here, right? So that's 40602C. So let's write that down in here. So seed is located at this address 0 times 40602C. So this is the memory address where the time value, which is the seed value, gets stored in memory. Might be used later, so let's have a look what happens here. So to go back, it compares a variable 4h, which is one of the variables that is used in this function. The variable set to 0 here, and that variable, because 8 bytes, the key is 8 bytes, right? So it's safe to assume that the variable here is going to be the key. So it sets the key to 0, then it's somehow getting the first byte here, then it increases the position of the variable, and then it says, okay, well, is it 8? No, it's not 8 yet, so create another random byte. So it adds random bytes to the key. When the key is 8 bytes in length, it then moves on, and then it moves to the next function, which is probably the decrypt function somewhere. So we need to figure out what this loop does and how it works. So let's have a look at this function to see what this function does here. But ultimately, our variable, our seed, and let's write this down as well as we go, right? So our key is probably, because we're not sure yet, located at variable 4h. Now the 4h just means it's the first variable. The second variable would be located at 8h. Once you learn a little bit of assembly, it becomes more clear. So we assume that the key is probably likely, I would say, even located at var 4h, because there's only one variable here, and this is generate key. So it ultimately will return that value. So G, fcn.00401 dc0, and let's see what this function does. 40602C contains the seed. So here what happens is the seed value is moved into the EAX register, and then all kinds of things are happening with that. So we can see that EAX registers and multiplied by this value. Then this value is added to EAX, and then we're moving EAX into the actual seed location. Then we're moving the word again to EAX, and we're doing all kinds of things with it. So this seems to be generating some kind of byte for the now based on the seed, and then it saves it back into the seed location. So it changes the seed value, or the original value. So it shifts, there's A and D. So none of these instructions really do make sense in terms of, other than some mathematical algorithm or some kind of cryptography, or maybe a random function or something like it. So let's rename this function. Oh, seed is okay. So let's rename this function by pressing DR to generate bytes, generate key bytes. All right, and then U. This starts to make sense now. So this loop runs 8 times. So every time it runs, it generates a key bytes. Maybe key byte would have been better, 1 byte at the time, right? So ultimately, where is our key stored? Probably this location here. Now that we know what this does, let's have a look and go back into the previous function by pressing U, and have a look to see what happens after the generate key. So generate key is being created. So now we have our key. So this print message will print our key. So if we go here, so if we say G and then print message, we'll actually rename that to print key, right? Because it prints our key. And what does this print function looks like? This function looks like this. Generated an encryption key, length 8. So in here we can see the length being printed, and this very likely prints the key itself. And those are being put into variables here. So I'm going to assume that argch is the key and arg10 is the length. Argch. So press U, so that's the second argument. So we got first argument, second argument. So let's type U. And this print function so this is the length. Push 8 is the key length, right? So it's pushing that into the print message. And then it's pushing EAX in the message, the print message function, and that is the key. So let's go into the function again. Generate key. Let's go into this function, generate key bytes. So if we know the seed value, which we have, right? We have the seed value here. It was given to us. So this is the seed value. We should be able to derive the key byte value from the seed value based on this function here. So we can use that if we have any idea of when this original file, the PDF that we need to decrypt, was created. more or less, 2019 would be good. A month would be even better, and maybe even a day would be even better. Then we would severely limit the amount of possibilities. So if it's less than, say, 1 million possibilities, then it's entirely doable to retrieve the key using, a portion of decrypted file contents. So let's do that. Let's try and derive this key from this seed in our Python script. We can use this function and kind of regenerate this assembly code in Python and do the opposite to get the the key from the seed. I'm going to put this seed value in our original decrypt. All right, so let's create a new function called generate. Generate key from seed, right? And then it takes the seed value for that function, and then we're gonna 1, 2, 3, 4 return. What are we returning? We're returning the bytes key, right? So ultimately, this is what we want the function to do. It takes the seed and it returns the bytes. So that's a good way to start writing a function. What do you want it to do and what do you want it to return? So that's the skeleton of what we're going to start out with. Now we're going to generate the key the same way as the assembly code is generating the key. And then hopefully we will be able to generate this bytes key using this original seed. Right, so we don't need to do anything else here after this. We just want to print the result of this based on the seed value. So what we want to run ultimately is this. You know what? I'm gonna put a sys.exit here. Print remove me. Sys.exit. So we don't need to worry about any of this stuff down here. We're only going to test our new function, small components, make sure the component works before we move on to something bigger, right? And then here we need to import sys because we're now using sys.exit here, right? So we are going to use the seed here. Return bytes key. Now let's just try the basic skeleton is hello and see if that works. So save all, and now we can run our Python decrypt. So we need to go cd sans, cd elf scroll, and then Python decrypt. And we can see remove me. Bytes key is hello. It's doing that. All right, so let's do print because we want to see the results of that key. Hello. So all this does now is this runs that generate key from seed, and it'll give you the key here. And let's get the actual bytes. Because half of our key, or maybe even more than that, won't be printable. So we want to just see the bytes and not the text. So there we go. So 68, 65, whatever. Those are the byte values of HELLO. Now, we don't want the bytes key to be hello. We want the bytes key to be the actual key generated from this seed, right? So we've got the seed value. And let's see how we can create the key from scratch using the seed value. And the first thing we can do is we can reuse this bytes key actually up here, and actually this is a byte array that is empty, right? And this code here, if we do a u here, you can see that this variable here, variable 4h, which ultimately contains our key, is being set to 0, so 0 bytes. It's basically emptied, and it is being filled here using this call generate bytes. So we have done exactly the same in our Python. We say bytes key is an empty variable. So this variable here is variable 4h effectively. Then we're comparing the bytes key length to 8, right? And if it hasn't run 8 times, then we keep running, and then until it's run 8 times, and it goes out. So we want some kind of a loop that loops 8 times. So let's do for e in range 8. Right? 1, 2, 3, 4. All right. So for e in range 8, we'll do this compare and this include this increase here. So this line here for e in range 8 will automatically increase I, which this part does, and compare that to 8. So run it 8 times. So now we just need this bit here to be in the middle here. Makes sense? So we're effectively recreating this script in Python. Very, very similar, very as close as we can to the original source code. So let's go into this function. So select this one and then G, generate key bytes. So the first thing that's being done is in this loop is we're doing some stack stuff, push EBP, pop EBP, don't worry about that one. This is just basic buildup of the function. The main meat is from this mov here to this and EAX here. So these commands here are the most important ones. So first thing that happens is we're actually moving the contents or the pointer of the seed value into EAX, right? So we can do that in our function as well in Python here. So let's say EAX is seed. That's effectively what we're doing here, right? We're putting seed into EAX. EAX is seed. So that's the first line done. So then we have a look at the second one, and it multiplies EAX with this number here. So let's do as close as we can to to the assembly code. Let's create a assembly IML instruction, EAX, comma, and then 0 times 343FD. So now we just need to create that assembly IML, and we can create that here using a new function, diff, and then assembly IML. And what do we take? We will take 2 values. So let's take EAX and an operand. We're effectively starting to create some kind of an assembly interpreter here. And then what do we want to return? Well, we want to return some kind of calculation here. So the calculation we want to return is EAX times, because we're multiplying, right? Operand. And then because it's 32 bits, we just want the, we're going to AND that, this sign here, this one here. We're going to AND that with 0 times FFFF and then FFFF. That is 32 bits worth of bytes, right? So this 0FFFF. So we only retain the 32-bit value of that. So this instruction here, this function, emulates this IML here. So if we do this, EAX is assembly IML EAX times that value, then we should get the value in EAX, which is the IML. So that's the second line done. And then we have a look at the next one, add. So we're going to create another one, EAX equals. Let's do the same thing, right? Add, and then EAX, comma, what are we adding? 0 times. 0 times means it's hexadecimal. 269 EC3. Oh, 3. I need to make sure that I use the right values. If you make a typo here, yeah, your key generated will be completely different to what you expect. So let's copy this bit here and create a new assembly instruction emulation. Add and then EAX with operand. And then instead of multiply, we're now going to just add AX with the operand. All right, and then we're only going to grab the 32-bit values again. That's really how simple it is. This is a multiplication. This is an addition, right, in Python. So now EAX contains this value here, which is the increased value by this hexadecimal number. So the next line here is we're moving EAX, that's the changed value, back into the seed value, right? So the seed value is now updated with that new value. And again, we can simply do that with this. All right, now we're saying that instead of this value goes into EAX, now we're saying EAX goes into this value. You know, seed goes into EAX, EAX goes into seed. Very simple. So we're literally recreating line by line what happens here in the assembly code. All right, and now we are moving. That's interesting. We're moving this number back again. So I'm not sure why we would move it, why we would do this twice. This seems to be redundant. So here we could say, okay, well, you know, this is the same instruction as above here. So let's do EAX equals seed again. But you can already see that's kind of pointless, right? We're saying EAX is seed, and then we're saying EAX is seed effectively twice. So we don't need this line. It's a bit redundant. Might be a compiler mistake. So let's ignore this mov, because it's effectively saying 1 is 1 and then again 1 is 1. Yeah, we knew that because we said that the first time. So move on to the next one. Here we're going to do a shift arithmetic right by 10. Right, so this is quite easy to program in Python as well. So let's do the same thing. EAX equals assembly, and let's call it SAR. EAX and 10. Let's copy this one up here. Let's use the previous one. And this is assembly SAR, shift arithmetic right. And instead of that, we're going to do, well, we're going to shift it right? So Python shifts right by doing these two greater than. So that bit shifts right. All right, so next line is AND and an AND, logical AND operation on a EAX with this value here. So I can write that exactly the same way, and I've got a few spaces in here. Let's remove them. Yep, so EAX equals assembly AND. Is it AND? Yes. And then EAX, comma 0 times 7FFFFF. And then we just need to create that AND assembly emulator up here. And you can see the program is slowly being built, slowly being created. And all we're doing is we're copy pasting a lot of this first bit here. And we're emulating assembly. So the AND operator in Python is the AND sign, just that one. So let's have a look at whether we're doing the same things here as in here. So we're taking EAX as seed. Yeah, so EAX is seed. Right, moving this value into EAX. Then we're moving the multiplication of EAX into EAX. So EAX is assembly mul EAX, and it is multiplication here. 343FD, 343FD, we got 406. Yeah, no, that's just a location. So we're adding EAX with this value here. So we say assembly add EAX with 269EC3. That's correct. And here we're adding using this plus here, so that's correct as well. We're then moving this EAX into seed, which we're doing here. That's this instruction here. This instruction is pointless because we're moving the same value in reverse, so it's kind of pointless. It's a waste of a CPU cycle. So we won't put it in here. And then shift arithmetic right, so assembly SAR, and then EAX operand EX 0 times 10, that's correct, and we're shifting right, that's the correct operator in Python. And then we're doing an AND EAX 0 times 7FFF, 7FFF. So assembly and, and this is an AND operator. So I think that looks pretty good. And then we're exiting this key generation. So we've now copy pasted this. So we just need to make sure that the bytes variable is now being set, right? We've done the loop. The loop has now been done. Now we just need to make sure that the bytes are actually written as well. So let's have a look at what happens here. If we press U, so we're looping. All right, so what's happening here is we're taking the lowest byte out of that 32-bit register. So if you see a 32-bit register might be EAX equals 0 times 1, 2, 3, 4, 5, 6, 7, 8, right? So that is a potential. I'm just showing you here in the Python script here. I'll delete this later. So this is a 32-bit register, right? I'm just putting spaces in between so you can see this is really 32-bit. So if we were to take AH, that would be this value here, and AL would be this value here, and AX would be this value here. Right, so let me just add EAX there as well. So you get a bit of an idea of how, you know, the assembly stuff all works, how the different sizes of operands work. So different register sizes. So EAX is the whole thing. I'll just remove the spaces so it's a little bit more realistic. There we go. So EAX is the whole thing, 32 bits. Right? This is 32 bits. AX is just the 16 bits here, 5, 6, 7, 8. So if I was to put this value into EAX and then get the AX value, I would actually just get 5, 6, 7, 8. If I were to get just the AH value, I would only get 5, 6. And if I were to get the AL value, which is what we're doing here, right? Get the AL value, then we're only getting the last byte here, which is 7, 8. So that's how that works. This goes all the way back to the 1970s, back to the Intel 8086, 8080 even, where you know, there were only a few registers, and then everything was 8 bits at first, and then 16-bit, and then we moved on to 32-bit, and now with 64-bit. So in order to stay backwards compatible to the previous programs that were written, or at least in an assembly level, assembly language level, they stuck with those AL, AH, AX values, so you could still retrieve, the 8-bit value, the 16-bit value, and the 32-bit value. So you could still compile, with minimum modification to your original source code, because it was really expensive to hire programmers back in the day. You could still run those programs that were created, and some of those programs were huge. So you could actually cross-compile some of the 16-bit code to run on 32-bit. So that's how far that goes back. Anyway, it still exists till today. So you got your AL value is being moved into ECX here, and is just taking that lowest value here. It is ANDing the value, so logical AND with FF, and then it's using that value, ECX, CL. So basically it's using that same value here. So we can summarize what's happening here below the generate key bytes as follows. So let's have a look. So in our loop, what we want to do is we want to actually save some of those bytes, right? So we want to save those bytes in the byte key. So bytes key, and we want to append to that bytes key. And you can do that with plus equals bytes, and then well, let's call it AL, because that's the lowest value, right? We'll try and stay as close as we can to the original source code, but we don't have an AL value yet. So what is AL? AL is, And then the only thing we're doing with the lowest value is we're doing an AND operation on that low value. So let's take the EAX value and that with 0 times FF. Let's use lower letters is fine. So what we're doing here is we're only taking the AL value here from FF, right? If I said FFFF, and this might not make sense if you haven't done a lot of assembly, and it might look really difficult, but once you get to know what AND does, you can actually get an idea of what's happening here. If I do FFFF, it would actually take the AX value, and if I did this, it would take the AH value. If I did this, then it would take the whole value. Right, so it just takes a portion of the content, because if you AND something by 0, it'll be 0. So this takes 0, 0, 0, 0, and then whatever the lowest value was in the original EAX. We've now done this bit here and this bit here as one line, right? For I in range 8 is this bit and this bit together. And then this bit here, we've kind of emulated here using various functions and assembly emulation. And then we take the lowest value, AL, here, take AL, we AND that with FF, and then we get that value, we put that into the key, the variable. Let's give it a run and see what happens if we get the same value. Good. So let's save this one here. Again, I try and start as low as possible in terms of scripting. If anything doesn't work, I want to fix that now before I move on to more complicated things. And we get an interesting result here, 5B31, 39, 30. So this is based on the numbers. 31, 39, that is actually just numbers. So 1, 9, 0, this 30, here's ASCII encoded. So it seems like I'm decoding a string into ASCII text. So, and that's what I told it to do, didn't I? Yes, so I'm getting the hex values of the actual encoded value. So let's also get the non-hex value and see what comes out of here. Oh, I should leave that there. We don't want to encode that. So let's see what we get out of this. Visibility as much as possible. We want to try and print as much as we can. Lots of prints in your code. Wherever you think, that might be going wrong, then yeah, you add a print and you go and check what the result is, what you get out of there. Now let's have a look first. Here you can see 1, 2, 3, 4, 5, 6, 7, 8. 8 bytes. That's a good sign. Makes sense because we did this 8 times, right? So we're running this 8 times. So now we just need to print this value in bytes and see if that's the same value, right? So one thing we can do is we can see 18. What is that value? So 12. And 12 hexadecimal is 18 in decimal. So this is the right number. So we now know that the this value here is the key. What we can do now is, if we had any idea whatsoever of the time that the document was created, and let's have a look at the web browser. Let's have a look to see if we can find any hints of when it was created. Here we go. Recover the plain text content, and we know it was encrypted on December 6th. So this is a very, very small time frame. So based on this, I'd definitely be able to brute force the key. So I didn't put this in here. And let's close this document here. Closing that one. Based on this time frame, we can very easily calculate the amount of seeds values. So we can use a range between particular seed values. Let's go into a epoch calculator to see what this date converts to in terms of time. This epoch timestamp is the lowest value, seed lowest, and seed highest. Let's have a look. 9 p.m. UTC. All right, so UTC, that is GMT. I think UTC and GMT are the same thing. Versus GMT, I think they're the same thing. Often interchanged or confused. That's good enough for me. Let's confuse the both and just assume that they're the same. So GMT here, and then 9 p.m. That's it. 666. Interesting number. Wonder if that was done on purpose or not. So we've got a really short time frame here and a very limited amount of possibilities. We could potentially have a look at the creation date of the document to see if that gives away anything else. But for now, we'll just assume that there's nothing there and try and brute force the key. You know, use it because we can generate keys. You know, we can generate every key between this number and this number using this function. And then we can try and decrypt the encrypted file, the PDF, using that function. So this I will put as a comment, so I remember where I got that from. We've now verified that our encrypted ciphertext works. We can decrypt that successfully. Now let's try and write another function here to decrypt files and see if we can decrypt our file, because I think we have a file somewhere, don't we? Oh no, we don't have a file because we've created that in Windows. It's not that much effort to create a file and just write the bytes because we have the bytes already, right? So we can write these bytes directly into a file and then we have the file. So let's do that. Let's do a quick search in Google. So bash create file from bytes. Google is very good. It just tells us exactly how to do things. So that's the question. This is the answer. So it says here, this is how you can write those bytes. And what bytes are there? So let's create let's use this file here. So that's what we're going to do. What are the bytes? Well, the bytes are ciphertext. Here we go. So these are the bytes. This way we don't have to copy anything. We don't have to insert a USB disk or connect network or whatever. So let's write that. Here we go. And then we can do a xxd test.text. Oh, do we have? Okay, I want to remove test.text because we don't use that. And then just in case, let's remove test.text.enc to make sure that this file actually gets created by this command. So xxd test. Here we go. So is that all the bytes? Looks like this is exactly the bytes we put into the original file. So, well, the encrypted file. So A6FC 59 D3 7C. To make sure that this is actually correct, because otherwise we're testing with something that might be incorrect at the at the base. The file needs to be correct. So now we've got the original file. Let's try and write a function in our decrypt Python that will allow us to decrypt this file using Python only without the tool, because the tool doesn't even run on Kali, right? So let's see how we can write that function. So we're going to call that decrypt file. And what do we want to return? Nothing. It just needs to return nothing because the file will be decrypted in this function here. So this function will write the new file. So for that, we need the file name. Let's take an input file name and an output file name and the key. So we take the input file, output file name, bytes key. That's all we need to decrypt the file. We have the file contents, so we need to read the file contents. Now for that we need to import the OS library. Let's open the file. Input file name. In read mode, read bytes. So RB means read bytes. So we're going to read every byte in that input file name, which we have to specify a little bit later, as in file. And then we're going to also open the out file. We're going to write that straight to an out file. Output file name. And then what are we going to do with that? Well, we're going to write the bytes, right? So write bytes as out file. Makes sense. So we're opening the file for read, and at the same time we're going to write the file. For every byte we read, we're going to write a byte to the file. A bit quicker, I would say. Out file write. So we're going to write for every byte that we read. Oh, we need some kind of a cipher. So cipher.decrypt, and then we're going to use the input is infile.read. All right, so we just need to get to create that cipher component. So cipher equals let's just copy it from here because we already had that function there. Bytes key, that's that one. The IV is 0, so we'll leave that the same. There's CBC, so that's correct. So this should open the file name, which we'll present later down here when you call the function, into an out file using the key bytes. So let's check that and see how we go with that. So we had a sys exit somewhere, didn't we? Print remove me sys exit. Okay, here we go. So we can remove this print command here. We know the seed there, and let's decrypt that. So let's try this function decrypt file, and then we're going to put input file, output file. So what is our input file and our output file? Well, input file is test.text.enc. And let's write that to test.text. All right. So what are we doing? We're doing input files that, output files that, decrypt file. We're going to do input file as per here, and then output file. And then what is our byte string? We've got our bytes key here, so let's move this whole bit under the bytes key so that we can access the bytes key, because we know this bytes key works for this input file. So let's see if we can decrypt that file now. So let's save that and run it. Okay, that's our sysexit. So let's see if it created a file. It did create the file, and the file is 8 bytes, so that's a good thing. So let's have a look to see what's in cat test.txt. And there we go. So we can see there that the test.txt.encrypted file was decrypted successfully using the this function. So now we've got a decrypt file function, but we still need to get the right seed value, right? So we need to brute force the seed value. So let's have a look to see how we can brute force that, and just create a function called brute force seed. Let's create the function up here. Def brute force seed value. And what do we want at the end? Well, we wanted to return the key, right? Oh, maybe just print something. We can print the key as well. Print key. All right, let's go like that. All right, so how do we brute force the key? Well, we need to try the seeds, every seed against the file, decrypt the file, and somehow get back the result. Now we don't know what the decrypted contents are, except we do get a small hint in here that it's a PDF. Now every PDF starts with the same header. So we have a bit of clear text. We know a PDF starts with a particular header to identify it as a PDF. And we can see that here if we open another PDF. Letter to LFU personnel, that's from one of the previous challenges we've done. If we do xxd minus help, we can actually specify the length. Yeah, so -L will specify stop after octets. So we want to only do the first 8. So we want to decrypt one block of 8 bytes of that PDF, right? So we're gonna let it be PDF and see. You can see here that every PDF starts with these 4 bytes, %PDF with capitals. That identifies this file as a PDF. And the benefit of that is if you do file and then letter to, then it says, oh, it's actually a PDF document for version 1.7. How does it know that? Well, file is not a magician. It knows it because it just reads the header, right? So it reads this header, %PDF minus 1.7. It says, oh, that's a PDF document version 1.7. If I change this byte to 1.8, then file would tell me that this is version 1.8. Right, so it just reads the header and it says, oh, that's a PDF. Every PDF starts with this. So if we decrypt only the first 4 characters of the encrypted file and we get this exact byte sequence back, so 25, 50, 44, 46, we can actually copy paste this already into our document. Then we know we've got the original PDF, and then we can use, whatever seed value we get from there, brute forced, we can decrypt the whole file. It'll be a lot quicker to decrypt only the first few bytes every time than to try and decrypt the whole file. And we don't even know what's in the file, because that's a challenge, right? To find the information in the file and to give them some, I think the first line or something, the first 5 words of the file. We have no idea of knowing what that is, but we do have some idea of what the first few bytes will be, which is %PDF, if it's a PDF. So let's copy those bytes into our progress file here. Elf scroll, I'll just put it in here. And in fact, I will put it straight in here because we know that we'll need it later. PDF header is bytes %PDF, right? We don't know if it's a version 1.7 or version 1.8. It doesn't really matter. If the first characters are decrypted to this exactly, then we can kind of assume that we have the original plaintext PDF for us, and we can then decrypt the whole file, the rest of the bytes as well. So the only bytes we need to decrypt is the first 4. So let's take, let's create another function. Before we create that one, let's leave that empty for now so that the compilation doesn't fail. Let's create another one because we need that header information, right? So let's create a function called decrypt file header. So what do we want this function to do? We want it to take a file in file. So we're going to put input file name and a bytes key, definitely. So most of this will be very similar to this one. Hey, let's take all of this, copy that in here. So instead of decrypting the whole file, we're just going to decrypt the first, let's say the first 4 or 8 bytes. So we just need to limit, because it'll be a much quicker function to decrypt just the header than the whole file. Technically, you know, the word header is probably incorrect. It's not going to decrypt the whole header. It's just going to decrypt the 4 first bytes. So we're going to read, let's say, and we don't need to really write anything out as well. We do need that cipher decrypt bit. Right, and we need just the first, say, 8 bytes, because we're going to decrypt 8 bytes. If we try and decrypt 4 bytes, it's going to say, well, it's not big enough to block, so we need 8 bytes. So encrypted. And then input file name dot read, and then let's say 8 bytes. That's a function to read only the first 8 bytes. If we wanted to read the first 100 bytes, we would do that. We just need the first 8. So that'll give us an encrypted byte string of just 8 bytes. We then need to close that file as well. So let's say input file name close. There we go. So we don't leave all those handles open. And then we need to decrypt those encrypted bytes, right? So let's print. Oh, let's just return that value. Then we can do something with it, because if we're going to brute force it, we can reuse that value. So we're going to return cipher.decrypt, and then not in file read, we're going to decrypt it encrypted byte. So that'll return 8 bytes. So this function will return to us 8 decrypted bytes based on this key here. So I probably should test that. So let's test that here now. I don't want to go too far and find out that my functions don't work. So we're going to use decrypt file header. We're going to use pretty much this one here. Input file. We don't need an output file for that. The bytes key. You know what? All of our variables are selected there, so I'm going to just put it here. I'm going to comment this one out because I don't want to run that twice. So we are going to decrypt the file header, the first few bytes of input file, which is test.text.enc, using this key, which is the right key. We know that's the right key. We're going to print the result of doing that and see what happens. All right, so what are we getting here? We're saying decrypt. So on line 38, 39, so we're getting an error saying read 8. Attribute error string object has no attribute read, so we can't read from the input file name. Let's have a look here, what's going on here. Oh yes, we need to open that. We're actually haven't opened the OS read here, so we're going to add that here. So F for file is open, and then input file name, comma, read bytes, and then we apply the read on F objects, right? So that'll work, and then we're going to close the F object. So we actually tried to read nothing. We needed to open the file using the os.open, which we're doing now. So we're opening the file, and then we're reading the first 8 bytes, and then we're closing the file again. So this should work a lot better. Save all, and go up here, Python decrypt. There we go. So the function header decrypt has decrypted tests, only decrypted the first 8 bytes. If this file was a lot longer, it would have still only decrypted the first 8 bytes. So we can decrypt the header, and that's a good thing, because we're going to look for, comparing that against percent PDF for the first 4 bytes, so we can brute force it. So we can now move to our brute force seed value, which can use our file header function in some kind of a loop between seed values, right? So we need, what do we need? We need a file name, first of all. So input file name. We need a header, like a %PDF, for instance. And we need a start seed. And a stop seed, right? Or maybe we should call them seed from, and you guessed it, seed 2. A bit more descriptive, I would say. We're taking an input file name, so that's the one that we're going to brute force the seed of. We're going to take whatever we're looking for, so a header. And then we have 2 values, seed from, seed to. That could be 0 to 1 billion, or it could be whatever this number is to this number. All right, so I'm going to get rid of this seed because we now know that everything works, right? So I can get rid of that one. This key can also go away. I'm going to make it a little bit simpler, this whole setup. Actually, no, I'm not going to do that. I'm going to brute force the seed. I'm going to try to brute force the seed value. I'm going to use some kind of a seed value here because I know the seed of this text file already. I know this is the seed value, but I might be able to test the brute force seed based on a number that is fairly close to this one. So a number range that includes this number that is not too large, maybe 100 or something. I go from 800 to 900. And see if it can brute force it. So I'll leave this all in there for a little bit just to see. So input file name. So what do we do with this? So for I in range, and then the range will be what? The range will be seed from to seed to, right? So that's what we're trying to brute force. So it'll only brute force anything between that range. 1, 2, 3, 4. I do miss Notepad++ in this regard, that it, I just press tab and it puts 4 spaces in, but yeah, you can't have it all on Linux. Actually, you can get Notepad++, but I didn't install it. So let's assume that the bytes key is generated from the seed. Bytes key is generate key from seed, and then I, right? So that'll start with seed from as the first seed. It'll generate the bytes key, and if that doesn't work, it moves on to seed from +1, etc., until it reaches the last seed value. So this will create keys from the seed value between this value and that value. All right. Generate key from seed I. Now, let's see what the decrypted value is, and we can use decrypted equals. Well, let's use this function here to only decrypt the header. So input file name is the same here, so we'll use that here, and then bytes key is that one. So we can literally just copy paste that in there. And now what do we want to check decrypted against? Well, decrypted, we want to check the first 4 bytes against that header value, right? Which should be %PDF. So if if the first seed value decrypts something that is not equal to PDF, it'll keep going until it finds that PDF file header. So if decrypted, and then I'll take the first 4 bytes, so 0 to 4 equals the header value, which is PDF, which we'll give it the header value later. Then what? 1, 2, 3, 4. Let's print seed found, and let's add that actual seed value as well to it, so we know what the seed is. So I will be the particular seed value. And then we return. We don't need to return anything here because they'll print that value. Let's take this function here, get rid of that one, brute force seed value, and then input file. What else does it need? A header. So that's the PDF header. And then it needs the seed lowest. Oh. And the seed highest. All right. Let's actually change that here so that they're all the same. All right. We don't want to use different terminology. Seed from, seed to. So that'll brute force the seed value of the input file. Now the input file for us is test.text.enc, and it won't find PDF, and it also won't find it in that seed range. So we're going to cheat a little bit, and we're going to say that the seed from is, let's say 800 to 850, right? So 828 sits in between those two numbers. So this we can temporarily, we don't have to comment it out because we're overwriting those values with these ones. So as soon as we delete them, we get the original ones back. So what we're doing is we're setting seed from is this, seed to is that. We know that the seed is in between those two values. So this is the seed it should be finding. The header that we're looking for is test, because that's what we should get, right? As the first 4 bytes. Let's comment out the bytes key. We don't need that anymore because we're brute forcing that, or at least we're brute forcing the seed. All right, we've made quite a few changes, but all the changes are kind of cosmetic, except this one. So we'll need to test this function out. So we're testing the brute force seed value function, and what we're looking for, instead of the header for the PDF, we're actually looking for the test header. It's not technically a header, but those are the first 4 bytes. So let's see what we get back and run this loop and see if that all works. Right, it doesn't. So line 50, return an indent does not match outer. All right. Key must be 8 bytes long, not 36. Have we tried the generate key from seed? I think we did. Regardless, we have the seed value here, so let's take that. Let's go back one a little bit. Again, if something doesn't work in here, just go back to testing each component, and we're gonna test this component here. So we're going to decrypt the file using the seed. So we know that the seed is this value here. So this should generate our key bytes, and we're gonna use this decrypt key here, decrypt file. Let's just take all that out here because the functions themselves will be fine. We will put our test function here, and then we're going to exit. And of course I don't want to rewrite all the test files and everything, so this is the point at which we are actually starting to do something, brute force seed value. So we're not going to do that yet. We're going to exit before we're brute forcing that. So we're going to decrypt the file using not the bytes key, but the generated key from the seed. All right, so that should work. If that doesn't work, then that would explain why this function doesn't work. And we might have to have a look at, you know, maybe that function, we haven't tested it. Okay, so we get the same error here. And now we get 35, 36. So I think that the way that we've put this bytes key here together might not be the right way. All right, so let's get just the bytes and find out how we can get those bytes. So what I'm going to do, return bytes key. That should be a byte string. That's definitely going to be the issue. I think we're quite close to getting it working, but we haven't tested this generate key from seed. So again, whenever you complete a function, always test the function. Make sure the function works before you move on. Otherwise, one of your components isn't working, and then you're going to run into issues later. So we're going to print the type of the output that we're getting here. So we're going to, and then we are going to just temporarily just comment that one out there. So let's see what the type is. It's a string. Okay, so we're looking for bytes, a byte array. All right. So obviously the way that we're saving this key is not right. So we need to save that as a byte array. So let's have a look to see how we can change this so that we get bytes instead of a string that makes up the bytes. All right, so let's check what AL is. So let's put a print here and then type AL, because ultimately we're adding all the ALs together into the bytes key. So something must be going wrong here. So let's do a save and type. So it's an integer. So we need to get the character value of the integer into the bytes. So I think instead of bytes, is to I think it's char or chr of AL. So let's have a look at that. I think if that doesn't work, might have to Google to see if that gets us what we want. Save. Type string. Let's print out. Apart from the type, let's also print out the actual key itself. And that should just be 8 bytes. Let's see how many bytes this is made up of. Non-hexadecimal digits found. So it is a string. It's adding all the string objects together. Let's review here in Google how to create Python int to char character. That's it. So ord. All right, gives not yet. No, but we want the other way around. So we want the character back to a string. So unique character. Python 2. I think we're using Python 2. So let's try use string unique character or string character, one of the two. Let's give it a go. Let's try that first because I think we are using Python 2. So that's still our code there. ASCII codec can't encode character in position, ordinal, not in range. All right, so let's just print that out and see what happens. Nope, so string unique car, maybe car. There we go. Type str. So let's see, now we know for sure that we're adding one character at the time. And let's see if that key is now being created. So let's try and brute force that, see if we get an error again. Oh, here we go. So it seems to be working now. So we just needed to change this output here. I'm not sure why I put bytes there. This is the right way to do it. So that seems to be working. So we can brute force the seed value now. So what we've done is we've just tried all of the seeds from this number here to this number here, and it found the original seed to be this number here. So the brute forcing does seem to work. So what we can do now is we can, instead of test, we can remove that. We can remove the bytes key because let's just remove it. Let's clean it up. The input file is going to be this file here, because now that we know that the brute forcing works, let's brute force the encrypted file here. Output file, we'll use the same output file but then .pdf at the end. We're going to find the PDF header, this one here. This seed to seed from, we know should be those two values. We can get rid of these prints. Get rid of that one. We can get rid of the cipher text, cipher and plain text. All right, so we're greatly simplifying the script here, removing all of the stuff we don't need, and let's have a look to see if we can brute force the seed, and that's very quick. So it thinks that the seed is this value. Oh, let's copy paste that here. So seed equals, and let's now try and decrypt the file using the decrypt file function. So we've just brute forced the seed. We don't have the key yet, but we can use our function generate key from seed, which we've just actually fixed. And we're going to enter the seed value there that we just got, which is this value 650. And we have an input file of that, an output file of that. So the output file is that. So just want to make sure that everything's all right. That we certainly don't want to overwrite our encrypted file. And this will decrypt the file, input file, output file, generate key from seed. Well, let's save that and see what happens. So done. ls-al xxd minus l8. Let's just decrypt. Let's just do the first 32 bytes and an elf-u research PDF. So let's do a file elf-u research PDF version 1.3. So it detects it as a PDF. So let's open that up and see whether we have the decrypted PDF file. It already looks like a PDF. It's showing us a PDF here. It opens it with GIMP. But that's all right. Apparently that seems to work. So this is the first page of our PDF. And the answer to the question was what is the 5 words in the middle of the first page, machine learning sleigh route finder. So let's try and enter that here in our game client. And let's submit that, and unlocked. So we successfully recover the clear text document.